When the U.S. Army needs to determine how many soldiers or officers to put in the field, they turn to mathematics. There's a system called the Manpower Long-Range Planning System that enables the Army to meet the personal needs for 7 to 20-year planning periods. So they have analysts who are able to effectively use these, we'll call them MLRPS, to simulate gains, losses, promotions, and reclassifications. Well, this type of planning requires up to 9,060 inequalities with 28,730 variables. But computers, they kind of help us out with this, and they can solve them pretty quickly. But the process that the computers use, the linear programming, can define the variables and create the inequalities, graph the inequalities, and determine the solutions for you. But there's got to be somebody out there who creates these computer programs to do this. So we want to know a little bit about how linear programming works. So when we do linear programming, we're going to be given an application problem. Yes, I'm sorry, we're going to have to read a word problem. The first thing we're going to do is define the variables. That means we have to figure out what the problem is asking us to find. A lot of times we use variables that represent the first letter of what we're trying to find. However, for our purposes, we're probably always going to use X and Y because those two variables are the ones we see most often. After we define our variables, we're going to write the constraints. We're going to be given a set of conditions upon which certain things can be done. Like you only have so much of a certain product, or you want to make more than a certain amount of product. So we're going to write inequalities to represent the situation. After we write these inequalities, we're going to graph them on a coordinate plane. Now, not on a regular coordinate plane. We're going to be drawing our own graphs by hand, and most linear programming problems occur in quadrant 1 because they're about making a certain product. You can't make negative product. You can't make negative cookies, so we're not going to be in another quadrant other than 1. After we do that, we're going to write an equation or a function to be maximized or minimized. That means we either want to find an ordered pair that's going to give us a maximum value to our function, or an ordered pair that's going to give us a minimum value to our function. Wait, those sound like things we talked about in section 2.6. After we do that, we're going to substitute the coordinates of the vertices into the function. So substitute vertices into function. And then we're going to select the greatest or least result. So let's get started and try a problem out that I'm going to walk you through. All right, in this example, a package delivery service has a truck that can hold 4,200 pounds of cargo and has a capacity of 480 cubic feet. The service handles two types of packages: small, which weigh up to 25 pounds each and are no more than 3 cubic feet each, and large, which are 25 to 50 pounds each and are 3 to 5 cubic feet each. The delivery service charges $5 for each small package and $8 for each large package. Let X be the number of small packages and Y be the number of large packages in the truck. So in part A, we want to write an inequality to represent the weight of the packages in pounds that the truck can carry. Well, the weight for the small package is 25 pounds, so that's 25x. The weight of the large packages, we're going to call it 50 since it's 25 to 50. And we know that the total, that means add, of the weight of these packages has to be less than or equal to 4,200 pounds because they told us that that's how much it can hold total. It can't hold more than that, so we can put less or up to. Now let's write an inequality to represent the volume in cubic feet of the packages that the truck can carry. So they told me that the volume of the small packages was no more than 3 cubic feet, and that the volume of the large packages was between 3 and 5, so we'll use the bigger number. And we know that the maximum volume or capacity that the truck could hold was 480 cubic feet, and that's a maximum, so we're going to use less than or equal to. The other thing I want you to know is we're going to graph this, but when we graph this, it is specifically going to be in quadrant 1. So I'm going to come down here and we're going to graph this. This is how I graph it. I just make a big old quadrant 1 because we don't care about the other quadrants. I'm not going to put little tick marks and call them 1, 2, 3, 4, 5. The way that I'm going to go about graphing this is I'm going to determine the x and y intercept of each of these inequalities. Then I'm going to go and determine what I would like to create as my tick marks. So the x-intercept, remember what you get when y is 0 is going to be 168. And the y-intercept, what you get when x is 0, is going to be 84. For the second inequality, the x-intercept is 160, and the y-intercept is 96. So I need some pretty big numbers, so I'm going to do some guesstimating here. My x-axis needs to go to about 200, and my y-axis needs to go to about 100. So I can do 20, 40, 60, 81, 20, 40, 60, 82. So we'll call each tick mark 20. 20, 40, 60, 81, and that's probably all I need to go on the y-axis. The first inequality has a y-intercept at about 168, so 100, 120, 46, so 168, maybe it's around there. And the y-intercept is 84, so 20, 40, 60, 84 is probably, I don't know, there. We connect the dots, the shading is underneath. The second inequality has a y-intercept of 160, which is awfully close to that, and x-intercept of 160, and a y-intercept of 96, which is awfully close to that, and they're mostly on top of each other. The shading is going to be down here. Well, now that I have graphed it, in order to maximize my function, which I haven't written yet, the function, if you go back up to the top here, we haven't done anything yet with the delivery service charges. The delivery service charges was $5 for a small package and $8 for a large package. So we'll call our function, I like to use p of xy, we'll call it 5x plus 8y. And in order to maximize that function, we need to find the vertices of our shaded region. Well, I know this is at 0, 0. Up here, the dot that's actually in the shaded region is the lower one. It's the one that's at 84. So it's at 0, 84. This one over here is at 160, 0. But, I mean, I drew a really bad graph. I don't know if the intersection is really there or somewhere else. How do I find the point of intersection of those two inequalities? Well, this is where I'm going to go use a matrix. It's already in standard form. So it's going to be a 2 by 3 matrix. Row 1 will be 25, 50, 40, 200. Row 2 will be 3, 5, 480. And then I'll RREF that. And I'm going to find out that wherever this is, it's at around 120, 24. So at least I know one of my other points on the feasible region is at 120, 24. So now let's maximize this function. I like to write it this way. So I write the function, I write the ordered pairs under the function, and then next to it I write how much money. Well, obviously, if I have 0 small packages and 0 large packages, it's going to be $0. If I have 0 small packages but 84 large packages, it'll be, my maximum revenue will be $672. If I have 160 small packages but no large packages, my revenue will be $800. And if I have 120 small packages and 24 large packages, my revenue will be $720. So which one of these maximizes my revenue? Well, it turns out it's better for me to have 160 small packages in my truck because I will make the most amount of money. Let's do another problem where I don't exactly walk you through it. The manager of a gift store is printing brochures and flyers to advertise sale items. Each brochure costs 8 cents to print, and each flyer costs 4 cents to print. A brochure requires 3 pages, and a flyer requires 2 pages. The manager does not want to use more than 600 pages, and she needs at least 50 brochures and 150 flyers. How many of each should she print to minimize the cost? Since the cost is what she's minimizing, my function, and I called it P of XY. I usually use P for profit and can do C for cost. You could use F. I don't care what you call the function. Is going to be 0.08x, because we'll call X the number of brochures. And we'll call Y the number of flyers, because I should have identified my variables first. So the the cost function is going to be 0.08x plus 0.04y. Remember, I want to minimize the cost. That means when I determine my inequalities, graph it, find the vertices, and plug the vertices into this function, I want to find the one with the smallest value. So the next question is, what are my inequalities? Let's start back with a brochure requires 3 pages, any flyer requires 2 pages. So 3x plus 2y, and we said that we don't want to use more than 600 pages, so we need to use less than or equal to 600. There's one of my inequalities. The other thing is we need at least 50 brochures. That means the number of brochures has to be greater than or equal to 50. And we need at least 150 flyers. That means Y has to be greater than or equal to 150. So we have 3 inequalities that we're going to graph. In order to determine what my scaling on my graph is going to be, I'm going to find the x and y intercept of the first inequality. The other 2 inequalities, remember, this is a vertical line and this is a horizontal line. So the x-intercept is going to be 200, and the y-intercept is going to be 300. So now I'll go make a graph. Nothing extravagant. So how about I scale my axes 50s? The reason is because 20, 300, 50, 150, it'd probably be best if I just do 50, 100, 50, 200, 50, 300. 50, 100, 50, 200, and then 50, 300. So, the first inequality we said has an x-intercept of 200 and a y-intercept of 300, and then I'll play connect the dots. This inequality is less than or equal to, it's going to get shaded below. X is greater than or equal to 50 is a vertical line through 50. Since it's greater than or equal to, it's going to get shaded to the right. So you can kind of already see where the shadings look like they're going to overlap. The last inequality is y is greater than or equal to 150. That's a horizontal line through 150, and it's going to get shaded up. So it turns out that my shaded region is right here. Well, how am I going to figure out what the ordered pairs of the vertices are? Well, this one's pretty easy. It's at 50, 150. If you're having trouble determining where this is because you made a hand-drawn graph and it's not awesome, I can tell you that it's on y is 50, so at least I know y is 50. What is x? Well, which equation is it crossing? Well, it's crossing that one. So if I plug in 50 for y and I solve the equation 3x plus 2 times 50, which is 100, equals 600. So 30x, sorry, not 30x, why did I say 30x? It's 3x. 3x plus 100 equals 600. Actually, I'm having lots of problems here. Let's try that again. Y is not 50, y is 150, and I keep telling myself it's 50 for some reason. This is 150. All right, so if y is 150, then when I plug in 150 for y, 2 times 150 is 300. And then I subtract 300, and then I divide by 3, and I find out that x is 100. So 100, 150 is that ordered pair. And then this ordered pair here is on the line where x is 50. So I know x is 50. So I'm going to go back to that same inequality, this one here, and plug in 50 for x. 3 times 50 is 150. Plus 2y equals 600. So 2y is equal to 450. And 450 divided by 2 is 225. So this ordered pair is at 50, 225. Well, I want to minimize my cost. So the last thing I need to do is I need to plug these ordered pairs into my cost function. So 0.08 times 50 plus 0.04 times 150 is going to be $10. 0.08 times 100 plus 0.04 times 150 is $14. And 0.08 times 50 plus 0.04 times 225 is going to be $13. So which one of these minimizes my cost? 50, 150. And my minimum cost will be $10. So this is how linear programming works. You find the variables, you figure out what they're asking you to find. They give you some constraints. These are the things you use to write your inequalities. You write a function that you're trying to find. A lot of times it's a profit function or cost function, but that's not the only thing we're trying to maximize or minimize. You graph it. Maybe you can figure out from the graph where the ordered pairs are. Maybe you use a matrix like we did in the last problem. And then you plug all your vertices into your function to maximize or minimize it.